All right. How you doing? Is it day pretty productive for you in terms of sessions, knowledge that you learned? Is it good? Perfect. That's really important because conferences is about knowledge and of course about sharing and networking. So I hope you got good networking, you got new knowledge as well, and you made it really productive. Okay, so let's start. First of all, thank you all for coming and welcome to this multiplayer Pac-Man presentation with RSocket. And I hope during this session you will have fun because this is last session in the row and it shouldn't be that heavy. So I'm gonna do my best in order to make it pretty smooth and enjoyable for you. All right, let me introduce myself. My name is Oleh. I'm from Kiev, from Ukraine. Have you ever been to Ukraine before? Oh, just a couple of people. For those who have never been at Ukraine, I'm welcoming you to Ukraine, to Kiev, especially to Deluxe Ukraine, which is tomorrow. So you have a chance to make kind of conference tour in different cities and countries. So I'm welcoming you. But in any case, welcome here. I work for Netify. This is basically a company associated with reactive programming and reactive streams. And I'm the person who loves reactive programming and reactive streams and Project Reactor and all these reactive libraries. I'm contributor of one of those libraries, Project Reactor. How many of you heard about Project Reactor before? Oh, great. Maybe RxJava? Some RxJava users? Okay. But in general, you have heard about reactive programming, right? Okay, because we will have some reactive programming, and I don't want to confuse you with some functional and declarative code. And a part of that, I'm a person who is working on an RSocket nowadays, and yeah, I hope I will introduce it pretty well. All right, a little bit more marketing. I wrote a book about reactive programming, so I'm gonna give away this one book to someone who will be most actively contributing to this talk, and a little bit later I'm gonna explain how we can do that. Okay, what about agenda? So first of all, we have to figure out what is the problem. And it seems from the first look that the problem is how to build multiplayer Pac-Man. But no, it's not a problem. Basically, there is lots of implementation of multiplayer Pac-Man. And today we are not going to look at how we can write the code and algorithm and so forth and so on. We're going to try to solve a little bit different problems. Because most of us doing the same thing today. And how do you guess what is the thing? How many of you are building microservices or distributed system or system which are communicating over the network? Just raise your hand. Right. Almost all of us building microservices, distributed system, or any kind of system which is communicating over the network. And today's the main problem is how to connect them. Because even though you're going to push your performance of the application to the maximum level, like you write pretty fast code, but then it turned that you have to send message over the network. And if it's not that efficient, you will start losing your money. I mean, you will start spending more money on cloud, on instances, and so forth and so on, and all of your optimizations won't cost anything. That's why today we are going to talk about distributed system and communication between them. And we are going to compare different protocols in order to figure out which one is the best one. And in order to make this comparison a little bit more engaging and interactive and more enjoyable for you, we are going to use multiplayer game as a source for doing that. Because multiplayer game is something where you have to send messages really fast with the lower latency, with the high performance. So this is a really good example and sample where we can compare different protocols and their performance. That's why all of you will have to enter at some point in time to the game, play it, compare different protocols, and then we all together we figure out which one is the best one. Does it sound good for you? Pretty well. So let's start and let's talk a little bit what do we want to build, or basically what we have already built a little bit in terms of multiplayer Pac-Man. So first of all, in order to let everyone play this game, we want to create some browser game, perhaps. So any browser have to have server. So we have server, and once we connect it to the server through the browser, it returns some index.html page, but it's empty usually because we want to make it super asynchronous and make all this additional data to be sent asynchronously without additional requests. So what we want to have in our application is kind of server-side push. So server will push everything that we need once we connect it to it. This is the first interaction step. Then, of course, once we got everything, we want to say, okay, I want to play the game. So I'm Oleh. I want to figure out who is playing right now so the server can return the current state of the game. And of course, in order to make this game like interactive, I have to somehow share my updates, my state, like what's going on my screen. And the most dummy implementation ever, I've done this, so don't blame me. I just send in every location and update on every step of my Pac-Man or Ghost. So this is the most simplest implementation. It just share location with other players. And of course, in order to listen to, for example, updates of me, we have to have some streaming from server side as well. So basically, we have to connect and listen for updates of other players. So it's kind of bidirectional streaming from client and server. And in this way, we're going to move our players. And of course, in order to make this game more interactive, like competitive, we have to have score. And of course, we have to have like streaming for scores and updates for scores in order to win this game, because there should be some competition. And basically, this is a place where you can contribute. So playing the game and getting the highest score, you will be able to win this book. All right. But so far, where is the distributed system here, right? You may wonder, this is browser, this is server, nothing complex here. Why microservices mentioned then? That's why in order to make this application a little bit more related to microservices and distributed system, and because we are trying to build maybe startup or something like this, we're going to add a little bit of trend words, some artificial intelligence, machine learning, and of course, in this way, we are going to try to at least earn some money or sell our company because we are super trendy, right? That's what we are doing at our startups nowadays. So basically, we are going to add some machine learning and artificial intelligence and teaching of the bots in order to then sell them like an algorithm or taught models for Pac-Mans. And for example, we have to collect some user actions. So basically, we're going to spy all the clients and collect the actions and movements of every player connected to the game server. And basically, in order to collect this data in any unclear situation, like really, in any unclear situation, you can just put Kafka in the middle, and it will for out for you, because Kafka is pretty high available solution. Then you will be able to push all the information to your Kafka, and Kafka will be able to handle it because it's pretty elastic and it scales up and down. And then behind the Kafka, we will have some small number of hardware computers, or I don't know, Raspberry Pis, which will collect data from Kafka, process them somehow, they gather data, aggregate them, and send to machine learning algorithm, which will process, reinforce, like continuously improve the AI and so forth and so on, and make for us money. So basically, at some point, it can work pretty well because it's this one server, this another. But this is distributed system. And the main point about distributed system is that it can work good, as well as it can work pretty slow or unstable. That's why at some point in time, our last machine learning server can work pretty slow. And we have to make sure that the whole system can kind of push back and continue working, even so one of the elements in the chain are pretty slow and unstable. So basically, let me summarize what I say. We have a couple of interaction models from the communication perspective in our application. So like server-side push, client-side streaming, server-side streaming, as well as request response. And a part of that, we have some part which brings or let us earn money, like machine learning pipeline. And we have to make sure that it works pretty stable, even though it's fast or slow. And because of that, because we have to earn money, we have to make sure stability of the whole system. All right. Part of that, as I said, I had something implemented. So let me introduce a little bit about technologies that we are going to use. On the backend side, we are going to use Spring 5. So how many of you are Spring users here? Oh, perfect. I like it. That's perfect solution, especially Spring 5. And a part of that, we're going to use Project Reactor, because Project Reactor let us write pretty efficient, non-blocking, and asynchronous data processing. Because our system is just a stream from here, from there, and then we have to kind of multiplex and demultiplex all the messages. So Project Reactor pretty fits well in this solution, keeping the high performance as a first-class citizen. And a part of that, we're using protocol buffer here. How many of you heard about protocol buffer? Okay, just a couple of, yeah, most of you, but for those who have never heard about protocol buffer is message format like JSON, but a little bit more efficient, like super efficient, because it's pretty binary and small and fast over the network. And on the front-end side, just for your information, I'm using Phaser for driving all this animation and movement of the players. So it's a game engine for browser. I'm using Reactor.js for the same reason of efficient data processing on the client side. And I'm using TypeScript because I'm a Java developer. I prefer static typing. That's why JavaScript is something I don't like. I prefer static typing. That's why TypeScript, basically. And of course, protocol buffer for balance between client and server. All right. In order to start just doing something, I decided to go with alt HTTP. You may wonder why. Why alt HTTP? Basically because it's pretty plain and simple. It's used for many, many years. And in order to build, for example, API and all the game logic with, for example, Spring Web Flux, you have to just do declaration of controller, add a couple of annotation, and then the magic happen. Right? That's what we are doing almost on the daily basis. However, the question is whether it's high performant and that's stable and solve the problem of smooth game experience for every connected player, right? That's why let's try together to play Pac-Man game, multiplayer Pac-Man game, and figure out whether Spring Web Flux is good enough for doing that. All right. So you can scan this link on the left side, for you it's on the right side, or you can use this short link like ESGD Web Flux. But in any case, let me copy this link. You will end up with something similar you can see right now on the screen. You will be able to put your name, and then you will see game UI, and you will be able to like do some gesture on your screen and play the game. And now we have to figure out whether it's good. Seems not that good, especially when I see that the ghosts on the left are jumping like a crazy. And yeah, it's laggy. So is it the same experience for every one of you? Is it lagging? Is it shaking? Is it not the super smoothie? Like I'm still trying to code the Pac-Man. You saw that. So in general, for some reason, it's slow and inefficient and maybe not the best experience for doing games, right? Is it the same? I hope this is the same like for you. Because if you're going to talk a little bit why HTTP is not that good, especially HTTP 1.1, we will figure out that HTTP 1.1 is text message based protocol, which means we have to send all the message in text format, which is overhead. And a part of that, it inefficiently uses our resources in terms of count of connection, because with HTTP 1, we had to create a new connection on every request. And you can imagine what will happen if you have to do TLS on every request, on every connection, which is super wasteful. With HTTP 1.1, it was improved, but in any case, you can create one connection, but pipelining sometimes doesn't work really well, so you have to create another connection and another, and sometimes it can like really create more than a single connection, which in any case, more load than you expect from your application, from a single browser, right? And this is lead to slower performance that you just observed playing the game. So a part of that, if you're going to think about communication patterns like doing request response or client-side streaming or server-side streaming, we will figure out that the only pattern we can do in the browser is request, response, request, response. Of course, there is some hacks like server sent event. How many of you heard about server sent event before? Just maybe 6 people. Right, because this is not that popular solution. This lets you create some server-side streaming to the client. Again, you can't create client-side streaming to the server. There is limitation, lots of limitation from the browser, which in any case leads to slow performance. And finally, the most important for me is stability. It's always about stability. And unfortunately, there is lack of stability in such kind of communication. There is lack of flow control. And what I mean, basically, I mean that flow control with HTTP looks like that. Basically, there is no flow control. Your client just sends messages until you die. That's what happened. And in order to survive, you either have to drop messages or you have to apply like retry logic because it's important to deliver messages and so forth and so. And again, you may wonder why. Basically, if you're going to look at the communication between client and server, this is client, this is server, so client sends messages, and yeah, sends messages until you reach the whole memory and your server start dropping all the kind of messages, which is for some cases unacceptable. Or either it's gonna die with out of memory because it got too many messages, which is also unacceptable. So basically what we need is backpressure. And backpressure, it's basically the way to control messages from subscriber to publisher. So subscriber should be able to say, I want to get like 100 of messages and not more than 100. Please send me only this number of messages. So if we're gonna have this kind of mechanism, like I'm telling how many messages I want to get, so publisher gonna produce exactly that number of messages, I will stay stably and will be able to recover from any disaster. So basically, yeah, those messages are gonna send and I process part of them, and I can request more if I see that I'm good in processing. So it can work really well. And this kind of communication pattern or backpressure is implemented in something called reactive streams. Have you ever heard about reactive streams before? Yeah, perfect. So basically, reactive streams is specification with a set of interfaces which does communication or streaming between client and server. And basically, the main idea is subscriber get a subscription, and using this subscription, it can tell how many messages it's ready to consume at this point in time. So it's clear that we want to have such similar mechanism in order to control our flow of messages. And now the main question, which protocols support it? So let's talk a little bit about protocols that we have today. It's clear that HTTP 1 doesn't work for us because it doesn't have flow control. So what else do we have? Probably HTTP 2, yeah? HTTP 2, efficient, binary, sounds good. Then we have TCP. TCP is pretty good protocol for doing game development and recommended for many, many years. Probably we can't use just TCP on the browser side, so we have to upgrade to WebSocket, which is exactly the same TCP, but over browser and server. And of course, we have some more exotic protocols like WEAK, which is not here yet. And we have like WebRTC, which is really hard in the implementation and usage. So let's stick to those two and figure out whether we can do something with them, right? All right. The next question is how to compare them. From my point of view, one of the important things about doing something about building software is to have good kind of development experience, or have a maintainable software, which basically it have to be a good framework with clean documentation. It should be like wide community support. You have to be able to Google and find an answer on Stack Overflow. This is about maintainability and good development experience. So we are not wasting our money on solving problems with particular solution. On the other hand, solution and protocol should bring stability into our application. So we are not going to waste our money because of disaster or unavailability of our service. Our application should work and bring money to our business. And finally, in our case, it's the most important characteristic, which is performance. So protocol should bring performance as a first-class citizen, and we should make we have to ensure that our application works pretty fast and efficient in order to bring good game experience. All right, let's start and let's try to compare them. Let's start with WebSocket. So basically, why WebSocket, you may wonder? Because this is the same TCP with no overhead. Like the only thing is additional flag with frame size, which is adding to WebSocket. And a part of that, it means that since there is no overhead, it's binary protocol, and which lets you send messages in a binary format. It leads to high performance. On the other hand, from my own experience, you may have the same experience as well. Building with a pure WebSocket is something really complex because you have to define message, because message is more than just a frame. Sometimes message could be a couple of megabytes or gigs. So you have to define message. Then you figure out that you have to define headers or MIME type or, I don't know, routing or whatever in order to route messages within the single connection. And then another challenge, and so forth and so on. And you ended up with reinvented application protocol, which does routing and tracing and whatever you need for your solution. And this is something less maintainable because you are the only company which support that. And this is a engineer which developed it, so at some point he is going to disappear from the company. You would have to deal with that, which is another challenge. All right, you may say, okay, there is existing solution, right? There is something like STOM and SOX.js which just let you do like pops up messaging back and forth, which is amazing. So it's application protocol on top of WebSocket. Or for example, there is Socket.io, right? So basically it sounds better. However, if you're going to do some more and more research, we will figure out, for example, that STOM is really outdated. The last update for STOM protocol was in 2012. Yeah, of course, it could be good, but we are in 2000 almost 20, and requirements has changed. So maybe this type of solution is not ready for today's problems. On the other hand, there is only pops up communication in those protocols, including Socket.io and STOM. So you have to define like request response pattern on your own, which is another challenge that you have to solve. And of course, there is no integration with Spring Framework, for example, which is important for us. And if you're going to look further and further and further, we will figure out that there is STOM for with Netty, which is pretty fast. But how many of you know how to work with Netty, with pure Netty? One hand, two hand, right? Almost nobody, because Netty is pretty complex solution. And if you're going to start working with Netty, you either became a super senior engineer or you fail. There are still options. So either everything is buggy, laggy, or too low level. So that's why we are not going to work with those protocols. And yeah, for some cases, Socket.io is not that well developed for Java. It works pretty well in JavaScript world, but almost every one of us is Java developer. So unfortunately, let's go look further. And the point here is that we need some good framework, good integration, for example, with Spring, in order to solve our problems smoothly without any like additional over-engineering. Right, do you know anything, any kind of protocol or framework which can simplify work for us? Any idea, my friends? Right, we have gRPC, which pretty good solution. I guess most of us heard about gRPC, and maybe if we're gonna ask why gRPC, we will figure out that gRPC is built on top of HTTP2, which means it's pretty fast. And if you're gonna Google what Google says about Google RPC, you will figure out that Google RPC is like from 7 to 10 times faster than HTTP, right? Sounds good. And then we will figure out that it works with protobuf RPC, which means that along with definition of your protobuf messages, you can define your API, like your RPC API, like this. And you can say, okay, this is request response, or this is, for example, client-side streaming. There is stream word here, which let you stream data from one side or from another, which is pretty cool. And you don't have to implement this API on your own. It's super cool because you can just say, okay, this is plugin to my kind of Gradle or Maven builder, and adding this plugin, you will be able to generate all this implementation of API without doing anything. And the only thing you would have to do is to implement the business logic. This is the most important, implementing business logic. Add one annotation, and you will be able to run it in Spring. Looks amazing. And finally, about stability. This is important for us as well. Google says it's stable. So yeah, again, if you're gonna Google what Google says about Google RPC, you will figure out that Google says it's stable, which is, yeah, sounds good. So let's try it. Let's figure out whether it's stable, fast, and that shiny as Google push it to us. Let's copy the link again. And let's figure out whether it works. So I put my name again. This is gRPC. This is gRPC implementation. Yeah, looks work. But yeah, let me find someone here. Let me expand. Still a little bit shaky. Still ghosts are jumping. And still I'm lagging, for sure, yeah. Especially right now. I just survived because the ghost jumped over me. So it's teleportation right now. All right, so for some reason it's not that shiny. And you may wonder why it's still lagging. Why it's still not that performant. I expected better performance. And if you're going to look at the, for example, development console, this is the first we can do in order to avoid any Googling. We will figure out that for some reason it says HTTP1, and on every step it still creates an additional request. So yeah, let me enlarge it. Yeah, do you see it? HTTP1. Why? Why? So basically, if you're going to Google what's happening under the hood, why gRPC is so slow, you will figure out that there is such architectural image which explain what's happening between browser and server. And for some reason, there is a web proxy, and this image says that you have to do HTTP1 or HTTP2 and to send the same request response in order to deliver your messages. And then this gRPC proxy will transform it into proper gRPC communication. Because basically, browser is pretty limited, and you don't have that low-level access as you can do that, for example, on the server side in order to do proper streaming. In browser, you only thing you can't do is request response using your fetch or whatever client, and that's it. Because browser is pretty limited, and specification even says that, yeah, the only communication pattern still is request response. All right. So basically, we figure out that we have to put envoy proxy, for example, in order to send the same request response communication, like sending location updates in the same way. And of course, we have to open a few more connections in order to get updates. This is something smarter which gRPC-WEB can do for you without doing anything on your own. But in any case, the answer is it's pretty slow. And that's why we are still lagging and shaking and so forth and so on. And we can't get the better user experience. However, someone on you can say, wait, it doesn't work pretty well in the browser, but for server side, it works pretty fast. There is binary HTTP2, which we can achieve without doing anything. So maybe we are going to use it on the server side, yeah, because gRPC said that it has proper like stability and backpressure, and we can use it on the backend side. And yeah, it's because of backpressure. And if you're going to look at the API of the subscriber, for example, this is a code from call stream observable, which is basically a subscriber side, we will see that there is this magical request method, right? That's what we wanted to achieve, and that's how we wanted to control backpressure. Yeah? However, don't be fooled by subscriber API and what Google says. You have to go deeper, learn what's going on the framework on your own in order to understand how it works. And if you're going to look at the API of the publisher side, you won't see any number requested from the client side. The only thing you will see is this is ready field. And do you see the problem here? What if I say that is ready under the hood is volatile Boolean? What can happen in multi-threaded environment with volatile Boolean? Basically, the racing can happen. And you can find the same issue on official issue tracker at GitHub. And someone complained about this racing behavior. An official maintainer of gRPC answered, yeah, there is racing. And unfortunately, gRPC can nothing to do with that. The only guarantee you can get from gRPC, if the isReady field is false, there is no guarantee that your application has already observed it. Courteous, we can say, okay, thank you, Google, thank you, gRPC, because there is a problem. If you're streaming data, there is a chance that we overstream some of elements because of this racy behavior. But yeah, it doesn't seem to be really a big problem. But what if we have more than one publisher in a single application, so every of those publishers can overproduce a couple of elements? In order to figure out the problem, let's try to run a test, real test on our part of the pipeline. So basically, we have our producers, we have some aggregation service, and we have our machine learning pipeline. And we remember that at some point in time, every part of our system could become slow. So we have to make sure that it works, so our components will survive in any case of disaster and won't die. That's what we want to check with gRPC. So basically, if you're going to run the test and make our server pretty fast, we will figure out that elements are going to send with the same speed on the client side as well as the same speed on the consumer side. So there is no problem. However, once we decide to decrease speed just in order to check the behavior, so there is balance. Once we decide to decrease the performance or stability of the right part, we will see that at some point in time, the consumer will consume less elements that producer produce. So there is some slowness in this part of the system, and there is racing, which causes this overproducing on the another part of the system. And basically, it's gonna stabilize at some point in time. However, in order to understand the behavior of the system, we have to look at the throughput, at real measurements and metrics. And there is throughput of publisher on the top, and there is throughput on subscriber on the bottom. And in order to see what's going on, what's wrong with that, we have to merge these graphs, we have to highlight them a little bit. And this is publisher, this is subscriber, and there is 20K messages in between them somewhere. Yeah? So the question is where? Basically here, in memory. Somewhere in memory. Yeah, of course, at some point in time, you can see like spontaneous increasement in memory usage at NetT, direct buffers, because under the hood, Google uses NetT. And it seems, okay, we got a few more gigs of memory used. What's wrong with that? But basically, we have to understand where we are doing, what we are doing today. And today, most of us are running containers, Dockers, whatever type of containers. And we're giving to them just a little bit of memory, a little bit of out of heap memory. And in general, if you're going to limit the number of resources, the next step that we are going to observe is the disaster, the out of memory. All right, so what we can say, of course, gRPC has some backpressure control, but yeah, this is not something we want to use in production. All right, so the last summary point for what we saw, anything either slow, hard in the implementation, and lacks some browser support. The flow control is not the best that we want to use in our distributed environment. And probably, do we want to solve all of this problem? Does our business want to invest money in solving all of this? Most probably not. The same happened at Netflix 4 years ago, almost 5 years ago, because at Netflix, you have like really big distributed system. And in their case, they decided to improve performance of the system using gRPC, sending all the streams to mobile, to TV station, to whatever, PlayStation, and any environment over gRPC stream, but over gateway. Because yeah, this is how we are building system. We have gateway, which let us connect to our internal system without like sharing some vulnerabilities to the world. And of course, there is some controllable server on the Netflix side, which could be scaled up and down. And there is lots of uncontrollable devices which could work really fast or slow, which basically led at Netflix to disaster and really fast died of the gateway. And you can listen to the real story from one of the developers who worked on this part of the system, and he reports that in their cases it just simply didn't work. Yeah, you can listen to the real stories. So basically what they done, because Netflix is a big shop of reactive programming, of reactive streams, they implemented RxJava for the first time in Java world, and they could do anything basically. They done lots of things like circuit breaker, rate limiters. So what they basically have done, they decided to implement proper protocol which follows reactive stream specification, which brings this flow control, and they call it this protocol RSocket. So basically, you may wonder what RSocket is then. RSocket, from my point of view, is something bright. The bright future of communication between microservices. All right, basically it's reactive streams as a network protocol. This is the simplest explanation of RSocket. Basically, there is this OSI model, like there is different layers of networking. There is like TCP, UDP on the layer 4, and RSocket takes layer 5 and 6, which is basically stands for session and routing. This is what RSocket brings to you for you. So first of all, instead of talking about RSocket, let's check whether it's better, because it could be another piece of, you know what. So let's make sure that it's faster and then going to discuss it. All right, let me copy the link. Let me put it over there. Let me connect and let me start playing. And here we go. Where is anyone? Here we go. We can see that Pac-Man is moving pretty smooth. Do you see that? No lagging, no shaking, no jumping like using teleport or magic tool. It just works smoothly. Yeah, sometimes it's lagging, but is it working better? Is it better? Just someone. Yes, much better. So let's go back to our slides and let's talk why it's better. Why it's faster, why it's more performant. Basically, the protocol is, RSocket is binary protocol. In general, it doesn't mean that you have to deal with bytes and count them back and forth. What you have to do, you have to decode your JSON or any message or Pac-Man into binary format, and then RSocket will take care of delivering the whole message over the wire and give you the same binary representation on the other side of the network. So you will be able to decode your Pac-Man in the same state without any problem. Then it uses the best from other protocols like HTTP2. So it uses multiplexing, which basically means that you can stream all of your logical streams and request response and request streams over the single connection. And RSocket will take care of delivering them in particular order and so forth and so on, add some additional identifier of logical stream. So you don't have to do anything on your own. The single thing that you have to do is to use reactive programming, for example, like Project Reactor or XJava, and send your logical streams back and forth. That's what you have to do. All right, the most powerful thing about RSocket is transport agnostic. Because with gRPC, for example, you are pretty bound with HTTP2, and this is a huge problem. With RSocket, you're not kind of bound to any particular transport from layer 4. You can use WebSocket, for example, in order to do the same browser-server communication with the same behaviors. You can do TCP just in case, or you can do Quick once it comes into the normal engineering, or you can use Aaron just in case you decided to build, for example, desktop Pac-Man implementation. So there is no particular bounds for what you can do with RSocket. Then it brings backpressure from reactive streams, and it means that if you send request, for example, 11 elements, this request will be transformed into frame, sent over the network, and then decoded back to the same number, and your publisher will receive the real number and will deliver the particular certain number of elements you requested, which brings really stable communication between subscriber and publisher. Then there is peer-to-peer communication, which was absent in HTTP2, for example. First of all, you have client and server, which we had to somehow establish a connection to the server. But once it happened, both of them turns into the peers, and they can do request one, and another can respond, as well as client can request server in the same manner, and server can respond back. So it's basically real peer-to-peer communication without any limits, and you can do anything even with your browser. All right, what about communication variety? You have request response. It's not only about streaming. You have fire and forget, like flash message out and forget about it. Request stream, so you have streaming from the server side, as well as you have like server stream to stream, so it's kind of client-side streaming or bidirectional streaming built into the protocol as well. And yeah, some notable feature which you can find useful. For example, there is leasing, which is basically let you avoid circuit breaker and rate limiter, because there is some handshake built into the protocol which lets server sell it capacity between all the connections. So clients know what was given to them, and they just do the number of requests that they were allowed. And a part of that, there is resumability. You can imagine you're building mobile applications. And the main problem with mobiles is that they connect, disconnect from the network, connect to Wi-Fi, disconnect from Wi-Fi, connected to 3G, upgraded to 4G. So all the time you are losing your connection, and you have to somehow continue your stream without any problems, without over-engineering. And you can do this really easily with RSocket because this feature is built into the protocol. So just say resume, and that's it. All your logical stream will be resumed after reconnection of your client. And there is fragmentation. So just in case you want to send big PDFs or whatever video in one message, you can fragment them into small chunks and having no problems and no headache. All right, let me show you some code in order to show that development experience is pretty good with RSocket as well, and let you know how you can start using RSocket, for example, today in Java. So this is the first example that we are going to consider. Basically, what you have to know as a developer about RSocket is two things. First one is RSocket. This is obvious. RSocket, this is the first RSocket. I can type it. Come on, buddy. What you're doing with me? Yeah, RSocket, Java. I want a Java. Come on. All right, let's do this other way around. Let's go here, and let's jump here. And here we go. This is interface RSocket. And RSocket stands for Client and Server API. This is a simple thing you can do. And then you can see that there is Reactor API and Reactor Mono and Fluxes. And the next thing that you have to remember about RSocket is payload, because payload is basically a representation of your binary messages. And it's not only about your data or message inside the payload, it also brings something called metadata or headers, which is built-in feature in RSocket, where you can put, for example, routing, MIME type, or whatever you want. And this is also part of the specification called composite metadata. Yeah, here we go. And in composite metadata, you can like specify, for example, MIME type or routing or whatever you want. So we have a bunch of specific things which you can start using, like routing, tracing, which you basically need in distributed system environment. All right, in order to, for example, define server, you have to use RSocket factory. So this is a start point. You can define a receiver or server and connector. So we have to have, for example, server exposed. You can use resumability. This is part of your builder API. You can say, okay, I want to use the main feature of native, for example, because we are using the main feature of native, like zero copying. So you don't have to copy the data you got from the network to your application to increase the number of objects for your garbage collector. You don't have to copy. You can directly access them out of heap and create super fast application. This is the main feature of RSocket, of native, for example. And you can specify, yeah, resumability, leasing, basically many things. We're not going to look at all of them. What you have to do next, you have to define your connection acceptor. So basically there is socket acceptor interface, which invokes this method once you got new connection to your server. And this connection is represented as an RSocket as well. So basically it means that this is real peer-to-peer, because here you have to return RSocket as well as you received RSocket. So basically you can do something like this in order to just let your client communicate with itself. Like this is a pipe, messages to myself. But of course we don't want to do that, but a part of that, client can send some setup payload and say, I'm Oleh, for example, and you can say, okay, you're authorized to do things. So you can check whatever you want. And what you have to do in order to start like defining some business logic, you can return abstract RSocket, which is basically implementation of RSocket, which returns error to any request. But simply you can override something like, okay, I want to return stream of messages. And here is the coolest part, that this is Flux. This is a stream of messages, and you can do something like login, mapping, and whatever you want, because this is a fluent API of Reactor. And that's it. Then you have to define transport. And as I say, transport is just an interface. So you basically can implement any transport you want. This is interface. However, we are bringing a couple of default implementations, for example, like WebSocket server transport, and you can say 8080 and that's it. Or if you don't like to use, for example, WebSocket, you can say, okay, TCP. And you don't have to rewrite the whole application using any other framework for doing that. You can easily switch transport and that's it. Magic, right? Amazing, I like it. Finally, you have to start your app. This is the simplest part. You have to start your application. Since everything is asynchronous, non-blocking, you have to block main thread in order to just keep your application running, and that's it. We can start our app, and it will expose 8080 port, and that's it. So this is the first part, and once we've done with that, we want to, for example, connect from the browser, because I said that the browser is a weak point for all the protocols. So here it's not a problem anymore, because on the browser side, we have the same RSocket server and client implementation, server for NOT, for example. But here we can use RSocket client. We can say, okay, we want to use WebSocket transport for doing communication with our WebSocket server, RSocket WebSocket server. And we are specifying link, saying some decoding for message, encoding, decoding, and then we specify setup payload. And here you can say, okay, this is my data MIME type, so it could be JSON, it could be binary format or text format, as well as metadata MIME type. And there is built-in feature like keep alive, pinging and ponging on both sides. This is a part of protocol, so you don't have to implement another part of the logic in order to check that your connection is alive. So this is a built-in part. And basically, you're connecting and you're receiving RSocket, and you can do request stream, for example. So let's take a look at that. Here we, let's go back to, here we are sending 100 of messages. So once we are going to open our browser, let me go back. Where is the browser? Yeah, here we go. Once we are going to open our browser, we are going to open development console. We will see that we received some messages. So we got a connection. So basically, this is the first log. And then we requested stream of messages, and we got some 10 messages. And you may wonder, why? Why 10 messages? Because we got like 100 of messages on the server side. Basically because of real backpressure. Because on the client side, on the browser side, we're receiving subscription. This is the most important part of Reactive-Streams specification. And now we can do request, real request. For example, we can change to 5. And if you're going to reload our app, we will see that we will receive 5 messages. Please recompile. Yeah, here we go, 5 messages. And if you're going to look at the logs on the server side, for example, let me just open it. On the server side, we will see that we exactly received request 5 over the wire. And we can do even more. The simplest we can do with a browser, we can do the following. Okay, I want to hack everything. I want to say, okay, window as any, in order to let my TypeScript compile. This is a downside of TypeScript. But I say, okay, my subscription. And I can put subscription into the field, into the global field, which means that I can have access to this field from for example, console window. And now I'm going to reload it, and you will see that nothing going to happen at all. Yeah, just connected. And now I can say, okay, my subscription request, for example, 15 elements. And here we go. We received 15 elements. I want a 1, 1. And if you're going to look at the logs, you will see that we're receiving exactly what was requested, like 15 and 1. Magic. Perfect. And even more. As I said, it's peer-to-peer protocol. So basically, you can do the following. If our business is going to fail with machine learning, we can always try to mine Bitcoins on the browsers. Yeah? Amazing business model. So basically, we can easily implement that logic without any problems. So for example, we have this sending RSocket, right? Which is representation of our client. And we can say, okay, please request for mining Bitcoins. Yeah, please mine some Bitcoin for me. We have to survive. And then on the client side, you can implement the same responder, the same APIs you've done on the server side, the same request stream or request response or whatever. And you can say, okay, I got your request. Yeah, I'm going to mine some for you. Yeah, all good. No worries. And then once we are going to restart our app, so let's do that. Once we are going to restart our application, yeah, restarting. Yeah, it's restarted. It's working right now. And we are going to reload. We will see, please mine Bitcoin. And here we go. Yes, I'm going to mine some for you. Amazing. Perfect. All right, let's go back to the slides and let's do the summary because we are almost out of time. What about API? Because this was just like plain RSocket, and this was layer 4 and layer 5 and 6, which is nothing about real API and routing and so forth and so on. Actually, there is RSocket RPC or IPS or GraphQL, which let you do real business logic and real API. And for example, in the case of RSocket RPC, you can use the same protobuf RPC. You have to just add one dependency. You have to just change a single library in the protobuf generator, and you will get the same generated file as with gRPC, which is amazing. But if you like, for example, Spring, if you don't like RPC stuff, but you prefer Spring Web Flux, and so forth and so on, there is Spring messaging. There is Spring Boot Starter RSocket, which is super stable, and you can just define a couple of properties and use your amazing annotations, and you will get everything working. Magic. I like it. So basically, development experience is on the good, really high level. All right. Actually, you can figure out that ecosystem is pretty big. There is different implementation. Basically, you can use any type of architecture. You can use any message format, and you can use any variety of transports, actually, which is super cool. What about stress and stability? Actually, like there is backpressure, real backpressure support. So client have to send, for example, 10 messages to subscriber have to send 10 messages request to the client, and only after that client will be able to produce messages. So in case something happened to your server, instead of just trying to push more data, server won't do anything for some period of time, and if it see that it's still slow, it will request less. This is how it works. And then clients produce less, of course. And if you're going to look at, for example, throughput and metrics, you will see that they're pretty identical on both sides. So it works stably everywhere. All right, what about advantages? Simplicity in development, pretty efficient resource usage, only a single connection for whole messaging, high performance, high flexibility in terms of communication patterns, and of course, first-class citizen efficient reliability. What about disadvantages? Because we are all engineers, and we have to understand what's happened once we start using RSocket, for example, today. Unfortunately, the main pain point is it's still under development, which means that there is no good documentation. There is 0.0.1 specification version right now, but we are close to do the first release. The implementation in different languages are with different versions, of course, and with different quality of implementation, which is also not the good for good development experience from that perspective. And unfortunately, there is not that many companies which are using RSocket nowadays. However, those companies who are using them today are pretty big and know what they're doing. For example, Facebook are using RSocket today in production, and all of you are using RSocket if you are using, for example, Messenger or any API or not API, but Facebook kind of web page. And this is RSocket C++. And there is more company like Pivotal, like Alibaba, like Netflix, which are using RSocket and having really good experience with it and like got lots of benefits in terms of saving money for their infrastructure. All right. A part of that, we created Reactive Foundation in order to improve and increase the community. So this is a good step, and pretty soon we will have more and more companies which are using RSocket, which will be using RSocket in production. Okay, what about final summary? Actually, you can finalize and see all the protocols like this. Every of them has its own kind of strong and weak side. For example, Socket.io works pretty well in JavaScript world, and there is nothing about that, bad about that. It just works. Like gRPC works pretty fast. Sometimes it overperforms anything that we have nowadays. However, if you want to build reactive system, stable system, where resilience is the first-class citizen, you have to use proper cloud-native ready solution like RSocket. All right, what to do next? Basically, you may follow my company and me in order to get more news about RSocket. If you want to ask some question, don't hesitate, go to community.netify.com, and we are more than happy to answer anything you want about RSocket. There is more video about RSocket protocols. You can listen other speakers. Or, for example, if you want to try RSocket in Spring, you can do that today without any problems. Finally, if you want to build some cloud-native application, like with all this future for enterprise, you can take a look at the last link. But this is basically it from my side. And now we have to define who is the happy winner, right? That's the most important, because I promised to give away a prize. So let's go and take a look at the postman and figure out who is the winner. So basically, the winner is this person. Who is that? All right, just come to me after the session and give you this book. First of all, thank you all for your attention, for coming to the session, and thank you a lot for being with me and learning RSocket. Thank you, guys, and enjoy the rest of the conference.